And it's only this thing inside the expectation, the function R and G, that depend on phi. So this term is not really easy to estimate by a Monte Carlo. There's a couple of things that you need. First of all, you need epsilon to be easy to sample from. And in our case, epsilon is really easy. Epsilon is just standard normal. You can sample from that very easily. You also need your R and G functions to be differentiable with respect to phi. And we also have that. So in this case, your phi is just your G is actually just a linear function with respect to your mean and sigma. So that's differentiable with respect to your parameters. And your R function, you also have to assume that whatever operation you do with Z on top of it is also differentiable with respect to your parameters phi. And we have that as well because we're working with these differentiable neural networks, and all these linear transformations and activation functions are differentiable with respect to these variation parameters. So then what you will get is that you will just sample noise multiple times from standard normal. Whenever you sample the noise, I'm going to put it through the transformation defined by these variational parameters, essentially multiply it by sigma at the mean to get the Z. And then I'm going to put Z through the function that I care about. That's going to give me a bunch of samples. I can now take the gradients with respect to phi because it's differentiable, and I can take an average across as many of these K samples as I want to approximate my expectation. So in our case, we can do that as well. So again, we have this evidence lower bound, which is equal to an expectation over Q log of P of X given Z minus the KL. We're going to just look at the first term for now. The KL is going to be basically the same. So again, we're going to change the expectation with respect to Q of phi to an expectation over epsilon. And whenever I sample this epsilon vector, I'm going to transform it by multiplying it by sigma and adding mu to it to actually get my Z vector. And now because of this expectation over epsilon that does not depend on phi, I can move my gradient with respect to phi inside the expectation. So again, expectation over my standard Gaussian samples, a gradient with respect to phi, and a log of my P of X given Z. And therefore, you can also approximate this using multiple samples of noise, computing this inner term and computing an average over that. So visually, what that looks like is that you started with X, you're trying to encode X into Z using your Q of Z given X. To encode X to Z, you also need your variational parameters phi. A naive method would be to encode, if we learn this distribution, Q of Z given X and phi, and then once you learn this distribution, sample entire vector Z. So Z is actually a random node. And once you sample a vector Z, you're going to go on to your subsequent functions, essentially going from latent variables back to your input. But then you will not be able to backpropagate your loss here over to your variational parameters because you have a random node stuck in the middle, which creates a bottleneck because you can't really backpropagate through like a random sample. So what reparameterization does is that it just samples a single epsilon. So this is where your randomness is. With this single sample epsilon, you're going to transform it according to your variational parameters to get Z. And then you can also put X. So this is your encoding function basically takes in X. It learns your mean and variance using your parameters phi. And then you're going to transform your random vector Z epsilon according to this mean and variance to actually get Z. So now Z is the deterministic function with respect to your variational parameters that give you your mean and your variance. So now that Z is a deterministic vector, you can use that to decode your image and define your loss function. And you're able to backpropagate your loss function with respect to Z, which is now deterministic, and also with respect to your variational parameters, which actually produced this mean and variance in the first place. So that is the reparameterization trick. So, just to summarize, we started with this log likelihood of the data. We saw that was not really tractable, and we derived this evidence lower bound, which is a lower bound to the actual true log likelihood of the data. And how good this lower bound was depends on this variational distribution that you chose. Right? You want this variational distribution to be simple. In practice, they're usually Gaussians with mean and variance predicted by your input data. So they're simple, they're easy to sample from, but in practice, because we're actually learning this mean and variance through your neural networks, they're actually very expressive, and they can also approximate your posteriors. And deriving this evidence lower bound allows you to optimize for two things. The first thing being this reconstruction objective, and the second thing being your prior objective. So in overall, how we actually learn a variational autoencoder, you will first take a data point xi, that's your input image. I'm going to define an encoder parameters, so a q of phi z given xi with parameters phi, and that allows you to take in, feed it xi and actually output a mean and variance that parameterizes q of z. So q of z is going to be a Gaussian with mean and variance parameters predicted by a neural network that takes in x through parameters phi. Once you have this mean and variance parameter, I'm going to first sample noise, epsilon from the standard normal, and then I'm going to compute the actual latent variable by a linear transformation of this standard normal multiplied by sigma plus mu. That's a reparameterization trick, which allows us to further get gradients with respect to mu and sigma, and only leave the randomness at epsilon. That allows us to get my actual latent vector z hat, and then I'm going to put z hat through a decoder with parameters theta to actually get the output, the predicted output. And there's two losses. One is a reconstruction-based loss between the reconstructed image and the original image, x hat and your x. And another loss is this KL term between your distribution of latent variables that you predicted using your encoder, that's q of phi z given x, and the actual prior which you want these latent variables to have, which is your p of z. So yes, so that is a full derivation of variational autoencoders going through variational inference. Again, most textbooks or most lectures will just directly give the autoencoder perspective, talk about the reconstruction in the prior, but many of the techniques here involving variational inference and KL divergence, they're useful in many other scenarios as well, beyond variational autoencoders. Cool. So now that we know what variational autoencoders are, we can talk about some of the applications of variational autoencoders, especially in these multimodal settings, which we all care about. So I think one thing, at least in the unimodal setting, just to begin with that, one thing which variational autoencoders are really useful for is learning disentangled representations. So what disentangled representations are is that you have all these images, and each of all these videos, and all these videos have very specific factors of variation. So in this case, only the floor is changing color. In this case, the background is changing color. Here, the circle is changing color. Here, the size of the circle is changing, increasing and decreasing. So ideally, you want to learn a generative model that not only generates these images, but it can actually generate these images with respect to these disentangled factors. So you want to be able to learn these factor representations, one of them corresponding to the color of the ground, one of them corresponding to the color of the background, one of them corresponding to the color of the circle, so that you can actually change and interpret these different factors that your variational autoencoder has learned. Another motivation for disentangled representation learning is that for style transfer. So again, in style transfer, recall that you're given a particular image with some content and some initial style, and your goal is to keep the content as much as possible. So in this case, the content of houses, you want to make sure you're still generating images of houses, but you're only changing the style of it. So essentially, many of these generative models for style transfer, these representations are disentangled into content variables and style variables. And then you can just manipulate the style while keeping content the same. And that goes for text as well. So how can we actually do disentanglement using variational autoencoders? You can actually do it very easily. So again, you have this variational autoencoders. Once you derive the evidence lower bound, you have this reconstruction objective, and you have this KL term that imposes the set of latent variables you learn to be as close to the prior as possible. So with suitable choices of the prior and suitable learning of this KL objective, you can actually learn these latent variables. You can actually learn this distribution of your latent variables Z to follow this prior. So usually what people do is that we can put a P of Z as standard Gaussian and isotropic Gaussian, which essentially means that across different dimensions of Z, there are no correlations. And if you impose this prior strong enough, what you're actually able to learn is a set of latent variables that are all independent from each other. So in this case, you want to learn one latent variable that's representing shape, independent from another latent variable that represents angle, which is independent from another latent variable that represents scale. So this autoencoders naturally, they actually already learn disentanglement just because you're imposing a prior which is disentangled. In practice, people have found that this set of beta VAEs, essentially having a tunable parameter beta in front of the KL, is easier for disentanglement. So if beta equals to 1, that actually covers your standard variation autoencoders, the evidence lower bound. For larger values of beta larger than 1, you're actually tuning the contribution of your reconstruction and your prior. And larger betas imposes a stronger constraint on the latent variables to have independent dimensions. So this is a very simple way of achieving disentanglement using variational autoencoders, which itself is a very difficult problem. We've seen both positive results for both text and images, but at the same time, there's a bunch of negative results, and also a call for better benchmarks and metrics to measure disentanglement. So feel free to look at all of these papers if you want to know better methods beyond this beta VAE and also better metrics to measure disentanglement. So one application of disentanglement is actually that for multimodal data. So this is a paper from our group, and the goal here is to apply these variational autoencoders for multimodal data with careful design of these latent variables. So in these settings, we're looking at these data with 3 modalities. So people speaking in front of the camera, with text, with gestures, hand gestures, facial gestures, and also tone of voice. And the idea here is that I want to learn 2 sets of factors. So one set of factor is a joint multimodal factor. And this joint multimodal factor, I wanted to capture high-level information across multiple modalities that correspond to things like sentiment and emotions. So things like sentiment and emotions are manifested in text, in visual, and also audio, and they're also used to predict the label. So that's the goal of this multimodal joint factor. And at the same time, I also want to capture these modality-specific factors within each modality. So a language-specific factor should model variations within language, different ways of saying the same sentence with the same emotion. And it also captures how different people say the same things with similar intents. So that would model things like this movie is great versus that movie was awesome. So the goal here is also to learn these disentangle factors, a joint factor, as well as these specific factors for each modality. So we can do that using a variational autoencoder. We can again define a generative network that takes in these latent variables and actually generates your data, as well as an inference network that takes in your data and actually predicts these latent variables. This is also called the decoder that decodes from your latent variables to your data, your encoder, which encodes data to your latent variables. So what this graph here is showing is basically you have a joint multimodal factor, that's your Z of Y, and this multimodal factor is in charge of predicting the labels. Right? You wanted to capture this shared information across modalities that are useful for predicting the labels. So it should be able to generate the labels. And at the same time, this joint factor, which contains label information, should also be able to generate your data. Right? You want your factor representing your positive sentiment to actually affect the generation of data from each modality to actually exhibit positive sentiment. And these modality-specific factors, for language, visual, and audio, they will not generate the label, but instead they will just model variations within each modality. So you're just generating within each modality. So that would model things like your language is going to be positive, but still there's many different ways of saying positive text, and that depends on person to person. So that's what these language-specific factors will try to model. And by using an autoencoder framework, again, you're going to end up with a similar set of losses, a reconstruction loss. So in this case, you're going to sum over each modality, the reconstruction within each modality. And this reconstruction is based on a set of two factors. Right? To reconstruct my language data, you will take in my language-specific factors, and you also take in this joint multimodal factor that tells you language is in general positive. So you're going to do this reconstruction of data within each modality across all three modalities. You're also going to have a prediction loss that estimates how well you're able to predict your labels from your latent variable representing this joint multimodal factor. And you're going to put also all these four factors together and stack them up. And you're going to impose a KL. You're going to try to minimize the KL between these latent variables as predicted by your model with a prior, which is a standard Gaussian, which to ensure that these latent variables have no correlations between them and are therefore disentangled. So by learning all these three losses, we're actually able to get really good performance using the discriminative factor. So you get much better performance than the baselines. But more interestingly, you're also able to do generation, which is one thing that your purely supervised learning discriminative methods are not able to do. So in this case, it's really hard to generate these high-dimensional faces and text and audio, but we use a simple example where one modality are these street view house numbers from 0 to 9, different ways of writing these 0 to 9 house numbers, and another one is MNIST, which is also 0 to 9, these handwritten digits. So you want to learn these, again, you want to define a generative model, where Z of Y is this joint multimodal factor that represents the label being 9. And for each of these modality-specific factors, you will have one of them representing the style of SVHN and another one representing the style of MNIST. So learning such a disentangled representation actually allows us to change each of these factors and generate my data. So if I just fix ZA1, so I want to keep the style of SVHN the same, I can change my label and actually get the same digit in the same style but across different labels, 0 through 9. And likewise, if I fix my my style factor for MNIST, I'm going to get the exact same style, but by changing my multimodal factor, I'm going to be able to generate different digits, 0 through 9, according to the same style. And likewise, if you fix this multimodal factor, which means that I wanted to keep it at the same digit, I want to keep it at digit 5, I can change my SVHN style and I can change my MNIST style independently to get different stylistic variations of the digit 5 in SVHN style and MNIST style. So that is a benefit of actually disentangling these factors so that you can do controllable generation with respect to each factor for these multimodal datasets. And another benefit of these generative models, which discriminative models do not have, is you're actually able to separate these factors, and you're going to be able to, you can measure the gradients with respect to with respect to the generation of each output, and therefore use that to interpret your data. So what I'm doing here is that the model is going to incur some loss in generating X1, my language modality, and I'm going to measure the gradient of that loss with respect to my latent variables, my joint multimodal factors. And what that essentially means is that it measures the contribution of this joint multimodal factor, which in our case represents things like sentiment and emotions, the contribution of that sentiment factor to the generation of each modality's data. So we're actually able to find that these gradients are actually quite informative in picking up these signals. So in this case, very profound and deep. That represents probably positive sentiment. And the gradient of the generation of those particular time steps with respect to my multimodal factor that represents positive sentiment was actually pretty high. Cool. So just one last application, another really cool application of VAEs for multimodal data. And this is quite different because it actually goes beyond reconstruction. Right? We looked at VAEs, we saw that they all have a reconstruction objective and also a prior objective, but this method actually goes beyond reconstruction, and they also found it to work pretty well. And why did it go beyond reconstruction? Well, in some cases, you don't care about reconstructing, and sometimes it might be also really difficult to reconstruct a high-dimensional input modalities, right? So if I want to learn a variational autoencoder to learn representations of video data, like reconstructing the entire video might be something difficult. So in this setting, what they were doing is, this was more for robotics. So it was the goal of trying to use a robot hand to complete some task. So this robot would have access to an RGB image of the position of the task. It will also have force data as measured by the robot touching the task and measuring the force exerted on the table, and also have some internal state of the robot that is constantly being updated. So you have all these modalities coming in. You want to learn an encoder that gets you a multimodal representation. And normally, if you just had a variational autoencoder, you would just have a decoder back to the exact same data. You try to reconstruct these high-dimensional images. You will try to reconstruct these long-term time series representing your force. You try to reconstruct this robot state, which can be these discrete factors. And that is in general quite difficult. So what they did was to combine VAEs with self-supervised learning. Instead of reconstructing itself, reconstruct some other signal which you know will be informative for your prediction. And these signals, if you choose them well, they can be much lower dimensional, but at the same time as informative or even more informative as compared to reconstructing the input. So what they did here was that they took this representation and decoded it into three things. One of this was optical flow, which another one was whether contact was made in the next time step. So that's a binary 0-1 variable. And another 0-1 variable which asks whether my force and my RGB image was aligned. Essentially, these are self-supervised quick signals that by domain knowledge you can actually define to be important for these tasks. So instead of reconstruction, they're actually learning encoder decoder that actually predicts these things. And at the same time, they're also going to impose a Gaussian prior on these latent representations. So what they found that firstly was these multiple modalities are pretty important. You want to be able to use both force and image to be able to complete your task. And at the same time, by having these multiple modalities, you're more robust to occlusions or imperfect data within a single modality. So you're using both force and vision. So you have external force, you're messing up your force sensor, you can also rely on vision. And likewise, if you have occlusions in visual, like these occlusions from a book, you can still rely on force to still complete your task. Cool. So that's it for variational autoencoders. We saw a brief introduction. We kind of derived the inference and training procedure and optimization of variational autoencoders. And we found that, well, in general, these variational autoencoders are easy to train, and they have an inference network, which means that for a new data point X, you can actually encode it into a latent representation that is useful for many tasks. For the cases of multimodal data, we saw that these latent representations learned by variational autoencoders were also useful for discriminative tasks and also useful for robotics tasks. One issue, though, is that variational autoencoders still rely on reconstruction. Right? We saw that it was a reconstruction term. In practice, people use mean squared error or cross entropy. They're trying to predict discrete outputs. And that still leads to blurry images. In general, estimating mean square error in high dimensions is not very informative. So if you look at these empirical studies, given particular image, variational autoencoders tend to generate pretty blurry images. But this new set of models that we're going to look at, called generative adversarial networks, GANs, actually generate much sharper images. So part 3, actually going into GANs. And I know LP talked briefly about GANs last Thursday, so I'm also going to go through just a really quick review and also more in-depth parts of GANs. So GANs were motivated by, again, the difficulty in evaluating and optimizing your P of X in high dimensions. Right? We saw that Gaussian mixture models, you could compute P of X exactly. For variational autoencoders, you could not compute P of X exactly, but what you could do was you could compute an evidence lower bound that approximates your P of X and therefore optimizes evidence lower bound. But GANs, what they do is that they just get rid of optimizing for P of X completely. Just because it's really hard to optimize, and even high P of X, as learned by the model, might not really correspond to realistic samples that your model is not fitting. So instead of optimizing for P of X, what GANs do is ask this really simple question. So let's say I have some samples of images that I know came from distribution P. I don't know what P is. I don't want to model P. I just know that it came from the distribution P. And I also have a bunch of samples of images from some other distribution which I know came from Q. So just based on these samples, without estimating P and Q, how can I tell whether it came from the same distribution, whether P and Q are the same distribution or not? And this has a lot of statistical theory, and a lot of these things work in low dimensions. But essentially, a lot of the theory behind this works through these things called two-sample tests. So given a bunch of samples from P and a bunch of samples from Q, the null hypothesis is that P and Q are the same distribution, and the alternate hypothesis is that P and Q are different distributions. So what you want to do is you want to define the test statistic to actually compare how different S1 and S2 are. And the very simple test statistic is just the mean. I'm going to compute the mean of all my samples in S1. I'm going to compute the mean of all my samples in S2. And if this, I'm going to compute the difference in means. And if this difference is less than a threshold, I'm going to say, no, the means look pretty much the same. I'm going to guess that P and Q are the same distribution. So I'm going to accept my null hypothesis. And if the means are really different, then I'm going to think, no, the means are so different, P and Q are likely different distributions. So I'm going to accept this alternate hypothesis. So methods like this are good because they're likelihood free. You don't actually involve the densities P and Q. You don't bother learning it. You just rely on samples. And GANs basically extend this where you want to train a generative model. So you have a distribution of your images from your data distribution, and you want to train a generative model to actually get P of theta, to actually sample more images. So given some real images from the data distribution and given some images generated by your model, I want to train my generative model to minimize this two-sample test objective. I want to train a generative model to make it seem like my data distribution and my model distribution is as close as possible. And these test statistics are really hard in high dimensions. Again, estimating means and variances in high dimensions are super hard. So what I can do instead is I can learn a statistic using a discriminator. So what I want this learned statistic to be is that the statistic should maximize the distance between S1 and S2 because I know they came from different distributions. And conversely, my generator should try to minimize the distance between my samples S1 and S2 because I want to make sure they look as similar as possible. So that in itself is our GANs. So it's a two-player game between a generator and discriminator. A generator will generate data from Z to X that tries to minimize the two-sample test objective. You want to make it seem like data and your model distribution are as close as possible. And a discriminator will be a classifier, a neural network that tries to distinguish real samples from the fake samples generated by the model. In other words, you want to maximize the objective and want to make it seem like the data to distinguish the true data from your data distribution and the generated images from your model distribution. So you can train these. Jointly. You can define this joint objective that for X from your real data, I want to maximize log d of X, and for X being from your fake data, I want to maximize log of 1 minus d of X. That's basically this binary classification loss. I want to minimize. I want to take true samples and predict them with label 1, and take fake samples and predict them with label 0. And if you really train this to completion, the optimal discriminator is going to take in a point X and actually evaluate the probability under your data distribution and see how close that is. So if it's really close if it's really high under my data distribution, this will tend to 1. And if it's really low under my data distribution, this will tend to 0. And that will correspond to a fake sample. So that's the discriminator. How would you train a generator? Well, the generator is basically the converse of that. Maximizing a discriminator, you will conversely minimize the generator. And the generator will try to basically fool the discriminator so that you cannot distinguish between the true and false samples. So you're going to want it to do badly at this binary classification task of assigning true samples to 1 and fake samples to 0. And if you do some math, you can actually find that if you retrain a discriminator, the objective function for the generator eventually boils down to this term, 2 times the Jensen-Shannon divergence between data and generators, data distribution and your model distribution minus log 4. So why is this important? So this Jensen-Shannon divergence is actually a pretty important term. So we've looked at KL divergence when looking at VAEs, which measure a notion of divergence between distributions P and Q. This Jensen-Shannon divergence is just another way of measuring divergence between two distributions. And this Jensen-Shannon divergence is actually very closely related to KL divergence in the sense that it's the symmetric KL divergence. You're going to take a KL between P and the average of P and Q, and you're going to take the KL between Q and the average of P and Q, and you're going to take the average of both of those. So it's also a divergence measure between P and Q. And that basically means that, if you have a discriminator, what you're trying to get the generator to do is to minimize a divergence measure between data distribution and generator distribution. Essentially getting your model's generator distribution to match my data distribution as well as possible, as measured by this Jensen-Shannon divergence. So there's a bunch of properties here. One interesting thing is, just as a thought exercise, why do we use the average of P and Q here, right? Why can't we just say Jensen-Shannon divergence as KL between P and Q plus a KL between Q and P and take the average between those? And again, that relates to the fact that, for KL, the support is super important, right? Essentially, you take this term, when you're doing KL, you the expectation over P, log P over this. This term is on the denominator, so this has to be, this cannot be 0 if P, this cannot be 0 for regions where P is 0, otherwise you'll be dividing by 0. So essentially, the average distribution between P and Q is done such that the support covers both P and Q, so that the KL divergence is well defined. And that essentially gives us the GAN training algorithm. You've seen this before when LP talked about it, but in general, you're going to sample some real images. You're going to sample some noise vectors. You're going to run these noise vectors through your generator to get some synthesized images. And you're going to essentially alternate the optimization of fixing the generator and optimizing the discriminator and vice versa. And you're going to optimize both of these parameters by gradient descent for the generator and gradient ascent for the discriminator. So the discriminator will try to best classify real images to be 1 and fake images to be 0. And the generator is going to optimize the opposite of that. It's going to try to fool the discriminator. And recently, we've seen a lot of improvements in GANs, most of which are essentially based on these loss functions. I think this was a very important paper that came out, which essentially looked at this vanilla GAN based on this Jensen-Shannon divergence and found a bunch of issues with it. So again, going back to this Jensen-Shannon divergence, I'm getting the figure back from KL here again. So for both, so Jensen-Shannon divergence essentially makes use of two KL divergences, right? And we know that for KL divergence, the support is really important, right? You don't want the support to be 0 in the denominator. And for many of these divergences, they're only defined on regions of Z, where both P of Z and Q of Z are non-zero. And you're going to measure the differences there. But the issue here is that, if my data is in really high dimensional space and my data lies on some low dimensional manifolds, then just starting with Z and just relying on gradient-based methods to get Z to a region of high support for Q and P is really difficult. Right? The true data manifold and my generators, my generated models data manifold can have negligible intersection in practice. And at regions where they're negligible, the KL divergence are either undefined or infinite, or it can be even 0. So that makes it really hard to optimize for Jensen-Shannon divergence as a metric between two distributions, your data distribution and your model distribution. So what this paper did was to introduce a different type of notion of divergence. It's called the Wasserstrom objective. This Wasserstrom objective is a different type of divergence. It's also called the Earth mover's distance. Essentially what it means is that, if I have a distribution looking like this and a distribution looking like this, how much mass has to be moved from this distribution to this? And mass is defined as the amount of mass times the distance which you have to move it from. So in this case, if this is 1 unit of mass and this is 1 unit of movement, then the Earth mover's distance here will be 1. So the good thing here is that it doesn't really care about the support. It's trying to move it across the support. If the support is far apart, that's just going to incur it into the loss. But it mostly compares in this direction, the amount of mass that you have to move to make one distribution into the other. And there's many good properties of Washington distance. I'm not going to go into all these details, but it's much more well-defined, even on high dimensional in high dimensions, and where supports do not overlap. And it's also really easy to optimize. It has a dual form, which is really easy to implement in the GAN settings. And just to get a good visualization, so assume this is my density of my real images, a Gaussian here, and here's my density of fake images. Because their supports are not overlapping, the gradients that you get for regular GAN, your KL divergence is 0 almost everywhere. So you're going to get very small gradients, vanishing gradients that are of 0 value, which cannot push your density of real and fake together to actually get something informative. On the other hand, your Washington GANs actually remains to get really good linear gradients that gives you a good training signal to bring this towards here and your density of fake towards here. Yeah, I think I'm out of time, but I think that was most of it. Next Tuesday, I will go more into some GAN applications, and I'm also going to talk about some reinforcement learning applications. So just a quick roadmap. Today was mostly about GANs. I think GANs and VAEs for continuous space for images, and we'll soon realize that you're going to apply these VAEs and GANs to discrete space, such as that for generating text. You're going to get a bunch of issues. And that's where some techniques of reinforcement learning will come in, which is that allows you to compute these gradients of the discrete data much more easily. So next Tuesday, we're going to talk about reinforcement learning. And then on Thursday, we're also going to talk more about reinforcement learning and introduce this technique called policy gradients, which will allow us to revisit many of these generative models for discrete outputs, which need to be optimized using policy gradients. All right, thanks everyone.